Simple harmonic motion. What the heck is that? Well, we're going to find out. So it is what we call the kind of motion when you have a mass that's basically moving back and forth against a spring, stretching and compressing a spring. Right? So it can be up and down like that, which is more complicated because of gravity situations. But it kind of just goes without, you don't have to analyze the gravity part of it. The simpler version that I wanted to show as well would be here. You can have a mass that's just going back and forth as well. And hopefully the other applet I'm going to show will be able to work still. It's a time limited thing. I'm not sure if it's going to work. Anyways, this one's kind of neat though too, because it shows what the acceleration and the velocity is each time. So watch when the velocity is in the middle here. It's unfortunate they make the scale so you can't see the actual size of the velocity, but the acceleration is the biggest one that blocks at the edge, and the velocity is the biggest when it's in the middle, right? You can just tell by the motion too, but something to analyze and think about. Here we go. Hopefully the other applet works. So we're going to look at some characteristics of these mass spring systems and this so-called simple harmonic motion. So simple harmonic motion, when you have masses on a spring, let's go to masses on a spring. And we need volume here. I don't know if there's going to be volume or not. So this is same springs, and what you have is a light mass, a small mass, a medium mass, and a largest mass. So at the start, you can see they are hanging. I'm not sure if that's the very start or not here. Yeah. So they're hanging, and this one stretched the farthest because it's the heaviest mass. And now let's just look at the frequency that they go at. You can see that the lightest one has the highest frequency, and the heaviest one has the lowest frequency. Okay, so that's something that I would just show in class normally. I just decided to find a video instead of making my own. And the other one would be the next thing we're going to ask or look at as well. So we know this now. More mass means lower frequency. And then the other question is, what about the spring constant that we know about from yesterday's lesson? Okay, so with a higher spring constant value, with a stiffer spring, what does that look like? Okay, so spring masses on springs with different K values. Here we go. So this one has sound. Let me just. That works. So this guy is kind of funny. He's like, I don't know if there's sound actually. When I first saw it, I didn't hear I didn't have sound on. So it's like he's miming basically the way he's doing it though, right? So it's perfect. Anyways, he has the mass on that spring. And you can see it stretches down a fair ways and has that frequency. And then he's miming things. It's like too much oscillation, I think he's saying. And then he has this one. He puts it on there, and it's like not stretching very far, and so that's a high frequency. And then for some reason the video cuts off and doesn't show the next one, but I'm guessing the green one was just right. Probably stretched a medium amount and had a medium frequency. What we're taking from that though, stiffer springs, that stretch less, have a higher frequency. All right. So what would the graphs of the repeating spring motion look like? And we're looking for the graph of the displacement from the so-called rest position. So wherever this spring would just rest on its own and come to a stop is the normal height. And then if you pull it down, it goes down from that spot, and then it swings up from that spot, right? So it's going above and below the rest position. Same thing here, the rest position being in the middle. It's going to bounce to the left and the right of that. Okay, so we're talking about displacement from rest position. Well, again, I mentioned before, we noticed that the speed of the mass is the greatest when it's at its rest position, right? So if the speed is the greatest, it's going to have a steep slope on the graph. So we're going to have a steep slope, something like, some kind of steep slope there, right? So that's this one, steep slope at rest position and so on, moving fast. And then we're going to have the speed getting slower and slower as it goes further and further away from the rest position, right? And so as we go away from the rest position, we're going to have a slower and a slower speed. And then at max displacement, the speed is zero, right? It comes to a stop at the very end or a very edge or very top. And so then you have that, right? And so we have that kind of shape. That is then, of course, going to reverse, going the other way. And so you can picture it going faster and faster on the way back, and then getting to the fastest speed there, right? Somewhere like that, they connect, right? And so we get this kind of shape where you can picture the result being something like this, right? And then of course that's just going to repeat again the other direction and so on, right? And so you can picture this curve that we get, right? That shouldn't be too surprising to see that in the applet next if it works. So this is what we call simple harmonic motion, okay? And it's sinusoidal, your trigonometric stuff from grade 11 math, sine and cos and so on. You can use sine or cosine to represent the motion. Okay, so there's some math tools there that we have. Let's see if this works here. I don't know if my time limit's up or not. Let's see. Maybe it's working. Yeah, we're working. Okay, good. So better work quick here though, but there's that sinusoidal motion, right? And the thing we can show along the way is important things like velocity. So see how the velocity is the most, the purple arrow, the most when it's in the middle, and then goes to 0 at the outer edges. So it's the most right now, and then 0, and then down the most, and so on. Acceleration, kind of the opposite, right? It's the most at the edges. That's when the spring is stretched the most. We're gonna have the most force from Hooke's law, and it's accelerating the least in the middle when the spring's at its natural position. Force matches that exactly, really. It's just different value by the factor of the mass. And then energy is kind of a neat one too, where they show like potential energy and kinetic energy, right? And so it has at the top here, let's go at the top. At the top, they're showing it as potential energy, which they're meaning gravitational potential energy. And then if I resume here in the middle, let's try and get the middle here ish, showing kinetic energy. That's where it has its highest speed, and so on, right? So at the very bottom, it shows potential energy. That potential energy would be the elastic potential energy. It's all stored in the spring, right? So energy is bouncing back and forth between elastic potential energy when it's at the bottom, all stretched, when it's gravitational potential energy at the top, all due to gravity, and then the kinetic energy when it's moving the fastest in the middle. Right, so really good analysis there of that kind of motion and so on. This page I just left in for fun. This is the applet I used to, or a little GIF or whatever you want to call it that I used to use. It's an old version, so apparently the new computer is faster. Anyways, but it is showing the same kind of stuff. Yeah, so with that applet, if it's still working for me here, we can change some things. Is that the one? Just go back here. Go to this one. Oh, that's why it's still working. That's not the one that's time limited. That's why. Duh. This is the one that's time limited. So let's see. Yeah, there you go. Time's up. Darn it. I was hoping because I logged out or turned the computer off, it wouldn't have kept going on me. But we already saw this stuff anyways. It's the same. It's repeat, really. Click the link yourself. You'll be able to use it for a little bit. If you crank up the K value, you're going to see the thing bounces quicker. And if you make the mass heavier and heavier, you'll find it bounces and the frequency's less. It's slower. Okay. So same stuff we've seen. And honestly, it's not even that great of an animation. So what we saw in the video is kind of more natural looking, of course, because it's a real video. Results from all of that, though, summarized here again for you. We know that with higher spring constant, we got this higher frequency. And so really we had that the frequency is proportional to the constant. And the larger the mass, we found that the lower the frequency was. And so it's inversely proportional, right? Frequency is inversely proportional to the mass. So that is stuff that we know, and we can watch for that in the equations later on, really. And so where are those equations coming from? This is the really cool part, right? The uniform circular motion stuff that we've done some good work to do with, we know lots about, have equations and so on, and simple harmonic motion have a link. So look at this motion of this blue dot going back and forth. It really is simple harmonic motion as well, right? So there's a fundamental link that we can take advantage of between the two. And so that gives us sort of a starting point in this class for getting an equation and understanding why the equation makes sense. So we're going to use that link, like I said, in circular motion. We know it's v squared over r. And for the circular motion, we know that the v is 2 pi r, right? It's the delta v, sorry, is 2 pi r. The v is 2 pi r over time, right? The circumference divided by the time. So we have this like fundamental equation that we know is true for these types of motion, right? So we got this 2 pi r over delta t squared and divided by r. And so if I'm squaring the top, I'm going to have the 2 squared, which is 4 pi squared and r squared. And then I'm going to have the delta t squared in the bottom. And when I have two fractions like that, I can write the this is like times 1 over r, right? So that's how the r is in the bottom of that fraction. So the r squared cancels with the r. We're getting that the centripetal acceleration, should add that in here. This is the centripetal acceleration, or the acceleration as it's going to just be called in this scenario. Yeah, that's our acceleration equation. And so if we're solving for the period, because we want to know the period and frequency information, right? So we're going to kind of convert this thing to just simple harmonic motion without the circular idea. So the time that it takes for a full circle is just the time that it takes for the complete cycle of the harmonic motion, right? Simple harmonic motion. So that complete cycle would be all the way up and then all the way down and back to where you started, right? That's the complete cycle, like you're used to from math class and from physics class and so on. This is the complete wavelength, if you will, from the waves unit from grade 11. If you haven't seen that, well, now you know it because I told you. But yeah, that's the thing. Think of a pendulum even going like from the middle, it goes out to the edge and then all the way back and then to the middle. And then after that, it goes out to the edge, all the way back and back to the middle, right? So we have this all the way out, which is this, and then back to the middle, and then all the way up the other way, and then back. And that's the complete cycle that repeats. So here we go. What's my next slide here? There we go. So yeah, we just keep solving here. Divide out the acceleration and acceleration concept. Take the square root of both sides, technically plus or minus, but we're just talking about time, so it's going forward. We have a reason to ignore the negative one. Fun fact, in quantum physics, they were ignoring the negatives and still do to most parts when they're solving, Schrodinger's equation and things like that, if you've heard of it. And there's some interpretations being thought about where the negative could mean backwards in time, and it's actually called the transactional interpretation of quantum mechanics. So the idea is the dilemma about the time, two actions being able to be related at distance with no times in between could be solved by the particles traveling backwards in time and so on. We're not there yet, but if you've heard of any of that stuff, it might mean something to you. Anyways, the period is 2 pi times the root of r over a, right? The r in this case is just your x, your value, your displacement from the center instead of the radius that the circle bounces back and forth, right? All we did there is root the 4, got the 2 outside, root the pi squared, got the 2 outside. No one in math is going to leave a pi squared inside of a root. They're just going to simplify it to just be pi outside of the root, right? So converting, right? This is the official conversion to simple harmonic motion, right? We're just going to have the acceleration and the time and so on, right? For simple harmonic motion. So this is where we get into it here, where we say, well, for simple harmonic motion, we know we've got F equals ma, and we know the force in simple harmonic motion is kx. So we have the force is kx and net force is ma. So we can solve here and end up with, by dividing out and so on, we end up with x over a. Well, the x is really the r, like I said, right? So r over a is really m over k. Just weird, but I mean, that's what it is. And so we end up with this equation. We have the period of a mass bobbing up and down on a spring is 2 pi times root of m over k, where the m is the mass, the thing on the spring, and the k is the spring constant. And if we were to show some math steps, we get the frequency version as well of this thing. Looks like I don't have it there. Why do I not have it there? Yes, back here. Root. Everything's gone. 1 sec. All right, fixed. It was just grouped, so it disappeared. But yeah, the math steps, you're just solving. You're changing period to be 1 over frequency, which we know from previous courses, and If not, if you need to know about it further, message me, put a post in the help post or whatever. But frequency is number per time, right? How often you go to the store per week is the number of trips to the store divided by the week, right? The period is how much time there is between the two, basically, right? Because they did trips to the week per week or whatever. It's kind of weird, but it's the number divided by time divided by the number, right? So the time interval you're talking about divided by the number of trips to the store in that case. Makes more sense if you think about it in terms of a pendulum, but a pendulum goes back a certain number of times in a certain amount of time. And then if you divided the time by the number, you'd have the time per cycle. That's the concept of period, right? Time per cycle. So that's what that big capital T was. Again, hopefully you're familiar with that from grade 11, but I know some people aren't. So I thought I'd explain that. But yeah, we get this equation for frequency, and I just want to point out the weirdness or the craziness of this. These equations give the frequency and the period of simple harmonic motion that you'll get if you put a mass on a spring with a known force constant, right? So really, it's a calculational equation that gives you the natural frequency. So those that have seen this a lot in grade 11, I hope that's kind of a, mind blown kind of moment where you're like, oh, that's kind of cool, right? If we measured the spring constant of a spring by just pulling on it, seeing what displacement you get the spring constant, and we'd be able to predict the frequency that it would oscillate at if you hang a mass on it. Just, I don't know, I find that kind of neat. So without friction, this motion would keep going forever, but of course there is friction. So the more realistic version is this. A little video here quick, right? So you have a more realistic version is friction slows things down over time. So your sine curve, the amplitude just drops off as time goes on, okay? That's the kind of thing you want to visualize, and obviously why and so on, but they call that damped harmonic motion. The amount of damping, the amount of energy absorption is the damping. So you get that kind of look, right? And so friction gradually just absorbs that energy, steals the amplitude. That's where the energy is, right? And transfers it to thermal energy, right, in the surroundings. So it kind of gets lost. So that's what shock absorbers on a car do, right? They absorb energy so the car doesn't keep bouncing up and down and making it hard to control, okay? So soon, tomorrow, in the next lesson, we'll look at energy in simple harmonic motion as well, just kind of combine the two lessons. So here's a sample question for you. If you have a 5 kilogram mass, it has horizontal simple harmonic motion with an amplitude of 10 centimeters, convert that to 0.1 meter. Due to a spring force, it's a spring it's attached to that has a constant spring constant of 80 newtons per meter. Determine the frequency, determine the period, and determine the distance the mass travels in 8 seconds. So what that looks like, we would just look at the things we know and see that we have an equation for the frequency. So grab that equation, use it, plug numbers in, right? Get a value. I didn't even bother calculating. It's just like calculations, get a number. If you're then looking for the period, you could just say, okay, well, period equals 1 over frequency, right? So knowing that I talked about how frequency is number per time, and the reverse concept would be time divided by the number gives you the time for each one, right? So that's supposed to say period equals 1 over frequency. Or of course you could use the full-blown equation for period, but it would be a lot more work to do that. So anybody that knows about this simple connection between frequency and period would just do that. But of course that's going to give you the time for a full cycle. So just using the new equations, plugging them in, plugging the numbers in, right? And then the distance it travels in 8 seconds. Okay, so distance it travels in 8 seconds, this mass is going to go over and then back to the middle in one full cycle, right? So what you're looking at there would be the amplitude. So the amplitude is the maximum distance. That's what we were graphing earlier, right? I didn't call it amplitude then, but we certainly did in my class in grade 11. So the maximum distance from the rest position is your amplitude, how big of a peak that is. And then you call this one a crest, and this one's a trough, to use some of the lingo from grade 11. But in the end here, we have 4 of those amplitudes per cycle. So a full cycle is 0.4 meters. So all you would do in this case is say, okay, well, I got 8 seconds, right? Well, whatever that time is, you're going to divide that 8 seconds by the period. And that's literally just going to give you the number of cycles it goes through. and then that means you have that many, of the 4 of that thing, right? So basically, that number times the 0.4 would give you the distance. So all you have to do to get numbers is just crunch the numbers, use a calculator. Physics concepts accomplished. Numbers can happen later. But yeah, hopefully that makes sense. And yeah, as always, you know the drill. Thanks for watching.